the fact that the fact that we have different interactions affect the behavior of our systems, and we will do it at different scales, since another characteristic of complex systems is the fact that interactions that occurred at one scale then influences the behavior at upper or lower scales. So for example, we will describe natural ecosystems at the level. Sorry, I'm going to move the mouse in order to be so to see, or here it is. Okay, at the individual level, and we will also go all the way up, and also study statistical laws, statistical patterns. And moreover, as I was saying earlier, that in complex systems you can have transfer of methods and theories. We will try to build a bridge between natural and information ecosystems in order to understand not natural interactions, but social human behavior. But first, let's focus on ecological systems. Because actually the definition of ecology it also focuses on interactions. We can say that ecology is the science that deals with the general question of how living beings interact and with each other and the environment. So in this setting, the emergent phenomenon that we have here is coexistence, in the sense that we have a lot of in different species, very, very different, but are living together. And the main question in ecology is actually why there are so many species, why that biodiversity. Then these species are interacting in a variety of ways. We usually know the exploitation interactions, also known as food webs, so predator-prey relationships. They are very well known, but they are also another type of non-trophic interactions. For example, mutualism, where both species get some benefit from the interactions. The canonical example is pollination, and also competition that has the opposite effect on species. And then very conveniently, interactions since the early beginning of its study in ecology has been represented as complex networks. However, these networks usually encode just one part of the information of the whole ecosystems. And in the last decade or so, it has been an increased concern that we need to add more information on the network description of our ecosystems. For example, one way to do this is to also introduce a space in our description, in the sense that at the end of the day, our individuals are living in a 3 or 2 dimensional space. So of course, this must also count in some way for coexistence. And then another important concern is that usually the network description is done just taking one interaction into account. And it has been just in the last years where both theoretical and some empirical studies has been carried out in order to add more interactions simultaneously in our systems. So we thought that so we are in this thesis going to actually add in our network descriptions these 2 ingredients, starting with a very simple system with just one type of interaction, that is competition. And why competition? Well, because if you just focus on competition, you end up with a paradox. It is called the plankton paradox, in the sense that if you have a set of species competing for the same resources, you might think that one species is going to be slightly better than the other one in obtaining that resources. So at the end of the day, you will end up with an ecosystem with just the most competitive species. However, like in the plankton that's not the case. We have a lot of different species of plankton. And one of the possible mechanisms that has been theorized to resolve this paradox is that of intransitive interactions. So we remove our assumption that we have just one species that is slightly better than the other ones, and we'll let the species compete in a sort of rock, paper, scissors fashion, in the sense that there is not hierarchy between species. If one species outcompetes one, then a third one outcompetes that first species, for example. However, these systems usually leads to oscillations, which at the end of the day may end up in extinctions. So there have been proposed more refined models of intransitivity, but they are usually very, very complex, or very different to them test empirical experiments. So we thought that that maybe introducing this space component, we were able to disentangle a little bit better what's going on in an intransitive ecosystem. And what do I mean by adding space? Well, now we want to encode the information about the spatial location of our individuals that are competing. So the competitive interactions are going to be structured. And to tackle this problem, we are going to describe it with a network at the individual level, in the sense that each node is going to symbolize a spatial location where one individual lives. With a space, we also need to introduce the interaction range, which is the distance upon which species or individuals can interact. And moreover, these individuals are located in a space. And when we are going to explore the way in which that space is arranged. So we are going to place our species in networks from the order range graphs, where actually it has no spatial structure, all the way up until a lattice, which is a highly ordered space. So combining these three network models with a short range, with short or long range, we are going to obtain several network topologies to answer the question of how does coexistence depend on space. Our dynamical model is very simple. Basically, at each time step, one individual dies, and that it needs competition in the neighborhood. We randomly select two networks that will compete to place each descendant on that vacant node, and the winner is going to be chosen according to this dominant matrix, which has intransitive cycles. So it encodes the probability that species I will defeat species J. And with this simple model, we have obtained dynamical changes depending on the structure. We are able to recover oscillations in some cases, but in others, we also get rid of oscillations. And in order to characterize this change of behavior, we have just chosen one variable, which is the area that the trajectory of the species follows in the phase space. So in the sense that if the trajectory is oscillating, the area is going to be big. And if it's not, and it's more or less stabilized in one point, it's going to be very small. So we have measured this area for our different network structures and these interaction ranges. For the order range, which is the network which actually has no spatial structure, we do not find any change of behavior. We always obtain pretty big areas, so oscillations. However, this changes with our structure networks. For these two, there is a region here with short range interaction when we actually obtain this stabilization of the dynamics. And of course, now we wanted to know why the dynamical behavior depends on these structure interactions and sort ranges. In order to answer this question, we look at the whole ecosystems. Here we have the lattice for short range and long range interaction. And we saw that just in the case of short range interactions, mono-specific clusters appeared. And in the sense that they are patches where you just have one species. So inside them, actually the competition is reduced, because if one individual dies there, it's going to be occupied by an individual of its same species. So the short range interactions in structured networks allows the creation of clusters that reduce competition with, at the end of the day, create this dynamical behavior we have also tested to be stable. Sorry. Okay, so now we have seen how adding space we can stabilize and get rid of oscillations. However, this is a very simple system, and with just 3 species and one type of interaction. And as I have said earlier, there is an increasing concern in the fact that we are obtaining results just for one type of interactions. But what happens if we want to obtain results for a whole ecosystem? Well, the logical step is to study more interactions simultaneously. And in order to do this, we will increase our scale, our level of description of our ecosystems. And now we are going to study networks whose nodes are not individuals, but species. And this setting is very interesting to study these whole network properties. For example, this complex community with several types of interactions. For example, the species survival, in the sense that nowadays the environment is changing, for example, because of climate change. And these changes may alter these species interactions, which in turn cause biodiversity loss and cascade of extinctions. So from a network description, we are interested in see how does the ecosystem breaks, in the sense that we will like to see if, knowing the network structure, we are able to predict what species are going to survive and what species not, with due to an environmental change. Of course, this question has already been tackled in the literature, but the approach was slightly different. Basically, because they usually just take one type of interaction into account. For example, here in this work, they discovered the PageRank as a predictor of coextinctions, but just for food webs. So our research question here is to see how these predictors may change if we take simultaneously more type of interactions into account. In order to do this, we are going to choose a very simple dynamic for our system. This is the replicator equation. So basically, it tells us that xi, that is the relative abundance of species I, will increase if its local fitness is greater than the mean fitness of the whole population, and is in this fitness where the network structure and the environmental change is encoded. Let me explain it. So here you have alpha, which is going to be the interaction range. And if alpha is positive in a symmetric matrix, that means that the interaction is beneficial for those species. So remember, it's going to be mutualism. And if it's negative, it's a proxy of competition. And what we want is to start our simulation with a change in those alphas, meaning that it has been an environmental change. And then regarding the interaction structure, the AIE is in adjacency matrix. We have simulated our model in some random graph, but also in empirical network with several types of interaction. For example, this of the web of life, whose mutualistic part is pollination, and then these of arid ecosystems in Spain. So we simulate our replicator dynamics equations in those networks and track what species survived and what didn't. And then, as we wanted to know the possible predictors of survival for each species, we made a list of some of its node properties regarding centrality, like the degree, the number of neighbors that the species has, some other mesoscale measurements like the cluster coefficient, and also some signed measures, in the sense that measures that take into account whether the links are positive or negative. So now with this information, we wanted to obtain what predictor better to tell us the fate of a species. And in order to do this, which is analytically intractable, we use a very well-known machine learning method, which is the decision tree. So very briefly, the decision tree is a classifier that, given a set of properties, is able to obtain some rules. For example, here, that the competitive degree is greater than 3. And obtaining these rules, it's able to classify a species on its 2 categories, so surviving or extinct. And not only that, we have chosen this machine learning method because it's able to quantify the importance of each of these nodes properties in the classification. For example, starting simple, just with one type of interaction, mutualism in this case, the decision tree for all these predictors tell us that for these 2 networks that are the 2 examples of the empirical networks, the main predictor is the eigenvector centrality. And not only that, but this classification here in the confusion matrix, we can see that is pretty good. And we obtain a trend, in the sense that if we plot this extinction time of a species in function of its eigenvector centrality, we saw that the species with a low eigenvector centrality are the first one in going extinct. And this trend that is common for all type of our networks also happens in competition, but in this case, we have the PageRank as the predictor of survival. So for just one type of interaction, we obtain one universal predictor for all our networks. And the situation changes a lot when we finally add these 2 interactions together in our study. In that case, for example, here, now we have these new signed measurements. We see that there is not just one single predictor with a lot of importance. There are several of them. And if we just focus on one network, for example, the orange one, and change the rho, which is the ratio between mutualism and competitive strength, then the array of predictors that we obtain also changes. So there are not universal predictors that depends on the network structure. And at least we can say that usually the predictors that appear to be important are the ones that encodes also the signed structure of our interaction network. And this fact actually is like a little warning or an invitation to revisit the results that has been obtained just for one type of interaction, to see whether the fact that we are adding more information in our description may vary these results. And in these two chapters, as you may see, we have explored several dynamical models and theoretical results in ecology. So actually ecology is pretty rich in these models. So as it's a complex system, now in this second part of the thesis, we wanted to explore whether all this knowledge could be transferred to the study of social systems, of human behavior. So we studied information ecosystems, which is basically an ecological approach to the study of human behavior, of computational social sciences problems. Because at the end of the day, here you might find more similitudes than difference between these two images of competition. And jokes apart, what we have done here is to build a bridge between these two domains. So species in our natural ecosystems can be translated to memes and hashtags and users, because this information ecosystem approach it's convenient to study behavior in online social networks. So during this rest of the thesis, I'm going to focus on online social networks where we have two types of agents, our species, hashtags and users. And as a species has an abundance, then in information ecosystem, that abundance is translated to popularity and visibility, in the sense that popularity can be defined as the times that a hashtag is retweeted or it appears in posts, and the visibility of users can be, for example, its a number of users, of followers, and then regarding the resources that species are competing for example, in the first chapter, here the resources are going to be the user's attention. And I will return to user's attention shortly. Now, just to say that that I'm going to use also the level of description of the species in these networks, which has had some focus in the literature in the last year. So we are not the only ones to spoil the tools of theoretical ecology in order to understand human behavior. For example, during my thesis, what we saw is that at the same time that we have certain structure for natural ecosystems, we are able to obtain those same structures for information ecosystems. In what sense? In the sense that mutualistic systems, for example, here composed by two guilds, pollinators and plants, exhibit a nested structure, in the sense that there is a hierarchy of neighbors. We have generalist species and then specialist species. And with this bridge, we saw that considering mutualistic interaction between users and hashtags, we also obtained that nested structure. And we also were able to see how this nested structure changes among time. And now let's pause a little bit, and I'm going to explain you what does it mean that users and hashtags have a mutualistic interaction. So what I mean is that users and hashtags can pair each other in order to increase its visibility and popularity, in the sense that if I'm a user which is very interested in science, in my tweets, for example, if I'm in Twitter, I'm going to use hashtags that are related to science in order to those posts appear in feeds of people which is also interested in science. And in the same way, as people has a limited number of followers to follow, then I'm going to be competing with other users that are also interested in science for new followers. And hashtags, of course, also can be thought to compete between each other, in the sense that at the end of the day, I'm going to use one hashtag and not another. And with this setting, our next step was, okay, we have seen this nested structure, and now we want to not only obtain the network structure, but also the strength of this competition and mutualism. So we wanted to quantify these drivers in online social networks. And why online social networks? What is this problem with users' attention? Okay, the problem is that nowadays we faced a kind of cognitive bottleneck, in the sense that we have a lot of influencers, brands, whatever, ads that are trying to get our time, our money, our clicks, our likes. So our attention in these online social networks is a new currency, and it has been said that there is competition for attention. So we wanted to characterize this competition and trying to infer what is the driver behind this collective attention. And the study case that we are going to use is our Twitter datasets that revolve around an event, in the sense that we have a Twitter feed, and suddenly one event appears. For example, Spanish election, the Catalan referendum, or a natural disaster like the Nepal earthquake. So we have periods in which, no, I'm going to try it again. No, okay. So we have periods, for example, here in Nepal, where the network is calm, and then we have peaks of attention in that event, for example, because the earthquake is happening, so all the news outlets and people is tweeting about this event. So here we have in yellowish the events, and in blue the calmer period. And in order to study how competition and mutualism change in this kind of data set, we use this bridge and characterize the dynamics with generalized local equations and concepts inspired in niche theory, in the sense that here we have the evolution of visibility and popularity of users and hashtags, and we have a competitive term. No, we haven't. Okay, yes. Here it is, a competitive term in red. So users compete among users, as I have said earlier, and then a saturating mutualistic term between users and hashtag, where these interaction metrics of mutualistic relationship is encoded. So now I'm going to present you the methods that we have used to obtain this network and the strengths of competition and mutualism. And we are going to do this using niche concepts, in the sense that as the example earlier was that I'm a Twitter user interested in science. And so science actually could be thought that it's my niche. So the environment in which I'm thriving, I'm good. So we were able to obtain these topics of interest for each of our periods in our data set. For example, here we have for the past general elections, this is the day of this is a period of the television debate, and here we have 4 different periods. One with people these are the hashtags that revolve around just elections, the general official hashtags. Then another topic with hashtags that are only focused on the television debate, and then here other topics with another discussions that were going on. So we are able to give for each user and hashtag a vector that encodes their affinity to each of these topics, and then simply projecting this vector, so a dot product, we are able to obtain these matrices, in the sense that if 2 hashtags just belong to one topic, then they are going to compete for the same set of users. So their projection is going to be high, so it's competition. The same for users, and in the sense of mutualism, if a user and a hashtag are very aligned in the topics that they are up about, then they are going to interact mutualistically stronger. And once we have obtained these matrices, our next step is to see how this competition and mutualism changes during the periods, during all our data sets. In order to do that, we defined beta effective, which is the effective competition. So basically, the difference between competition and mutualism that the agents have, normalized with a baseline of mutualism and competition that they would expect for a calm period. So positive beta effective means that we are experiencing more competition than expected. And the results that we have are pretty robust for all our data sets, in the sense that in the peaks of the events, which are the gray regions, all the hashtags experience more competition, and the opposite case is for users. So users actually during peaks of attentions experiences less competition. How is this possible? Well, in order to first explain the hashtag behavior, we look at how the topics were distributed during calm periods and the peaks periods. And we discovered that actually during peaks, we just have 1 or 2 topics that englobes all the discussion. So during those periods, hashtags are experiencing a lot of competition because they are all competing with each other. And for users, the explanation is more subtle. And in order to get to it, we need to propose a driver for the user's behavior. And we also recurred to our ecological bridge, in the sense that in mutualistic communities, it has been proposed by Suez et al. That the nested structure that we have obtained comes from a process, which is the maximization of species abundance, in the sense that species are able to choose their mutualistic partners in order to increase its abundance. And we thought that maybe users were doing precisely this. They were choosing their hashtags in order to maximize their visibility. So we construct, so we started to simulate with these log-coupled equations and add this optimization rewiring process. And we wanted to compare the final mutualistic structure. This is the mean mutualistic value in the 3 peaks and a calm period. We wanted to compare these values with the values obtained with our optimization process, starting at the age of the event. And we obtained that the structure and the mean mutualism that finally the users managed to obtain was very similar with the one empirical. So we were confident to say that the driver that thanks to this bridge between ecological and information ecosystems, we were able to describe how competition and mutualism evolves during events, and to point the driver, which is the visibility, the optimization of visibility. And now this ecological bridge that has give us these results can also be used, applied at a higher level of description. And in this last part, I'm going to talk about another very promising part of ecology, which is that of macroecology. That basically it seeks for statistical laws, statistical patterns in ecosystem across very different geographical locations and scales, in the sense that big ecosystems and also macrobiome. These patterns are hold for all these type of different organisms. The patterns can be in abundance, in distribution, and why these patterns are that important? Well, because they precisely help us to find mechanism for its emergence, in the sense that if I propose a model to explain the distribution of species, at least that model must be able to reproduce those patterns. For example, here we have the species area curve, which basically tell us how the number of new species that we saw in an ecosystem increases with the area of that ecosystem. And of course, now what we want is to see whether there are patterns in our information ecosystem. So again, our species now are going to be our hashtags, and it's abundant the popularity. And in order to look for patterns, since ecologists have gone all around the globe to obtain very, very different ecosystems, we increase our number of data sets, and now we have 11 data sets that are, we hope, are very heterogeneous. They have very different number of posts, so different number of size, different duration, different number of interesting hashtags, and yeah, their profile is also very different. And the patterns that we are going to look for are 6 very well-known patterns in ecology, and I'm not going to go to all of them, but just let me present you 3. This is the Taylor law, which actually connects the mean abundance of species with its variance of species, of hashtags in this case. And the scaling that is proposed is with an exponent of 2. And what we obtain if we plot this the logarithm of the mean abundance with the variance, we will recover a slope of this exponent 2, which has also been found in other human structure, like for example economical firms with its sizes and those things. Then the one that I presented you earlier, the species area curve, with now recently has been found this ugly expression that actually with its parameters connects this pattern with another pattern. So we were also able to see how if we increase the sample size in our data set, how that scales with the number of different hashtags that we saw. And here in the graphs, you can see that the theoretical form fits pretty well with a lot of data sets, and in others, at least, there is a qualitative resemblance between these 2 trends. And finally, patterns can also be temporal. For example, this is the distribution of relative abundance changes between two times, which is proposed to follow a Laplace distribution. And in our case, our empirical dots also fits to this proposed distribution. So the message here is clear. There are patterns exist, and one thing that now from the presentation might be obvious, but actually is pretty interesting, is that the functional forms of the patterns are the same as the patterns found in ecology. I mean, for example, for the Taylor law, it could have happened that the slope maybe was a 4 or a 21, but no, it's also a 2. So that means that these patterns are universal both for ecology and for information ecosystems. And now, just wrapping up during this thesis, we can draw some general conclusions. So first, to the ecological part, with our work, we have reinforced the idea that interactions are one of the main drivers of coexistence, and it's very important to to increase the efforts to add more information of these interactions, to refine our models and add, for example, a structure or a spatial structure or more type of interactions. And then also regarding this bridge between ecological and information ecosystem, this bridge has allowed us to discover new drivers of human behavior and these patterns. And well, regarding these discoveries, of course, we already have some new research going on that has been inspired in these results. For example, regarding interactions, we are now thinking whether interaction modifications or higher order interactions also can maybe could be also a very interesting ingredient to explain coexistence in ecosystems. And then regarding these patterns that we have found, now that we have the patterns, what's the next step is to look for the underlying mechanisms that generate these patterns, that chances are that they are going to be the same or very similar to the ones that generate the ecological patterns. And also revolving around the collective attention problems, now that we know that there are patterns in this data set, we wanted to know whether the patterns, the parameters of the patterns, or even the functional form changes a little bit during events. And as you see, we have a lot of work to do, so I'm not going to get bored. And now I will be very happy to ask any of your questions. Thank you.
Thank you very much, Violeta, for this excellent presentation. It's time for question now. And the first term is going to be for the professor Vincenzo Nicosia. Vincenzo?